All right, go ahead, Julian.
All right, thanks, Frank, for the intro. Yes, like Frank said, I'm affiliated with the University of Sydney, where I work in the computer science department. But I also spend some time seconded over the last 4 or 5 years with Meta, where I try to apply all the stuff that I learned in my academic life into real products, and trying to bridge that gap between theory and practice. So this is a paper that was published last year on a problem that came from a very down-to-earth application. Okay, so the problem that we studied is called the extended TSP problem, and I'll tell you a little bit about what the problem is about. But before I do that, I want to tell you where this problem is coming from. So this problem is coming from an area called profile-guided optimization. And this is something that I've been working on at Meta. So at a very, very high level, profile-guided optimization is a technique that it's used in modern compilers, where you leverage profile data about your applications, and you use that information to restructure, recompile your programs, and get more performance out of your services. Let me get this out of the way. Okay. So this is an area that is actively studied in compilers. There's a lot of work, but our starting point goes back to an old paper by Vertex and Hansen that introduced the concept of block reordering, and they formulate this problem as a maximum TSP problem. So what is this problem? This problem is basically the following. When you write a computer program, you have all these instructions that the compiler translates into machine code that the machine can execute, right? So if you think about your computer program, your typical computer program, you have instructions like fetch me the value of this variable, add it to this other variable, store it into this variable, multiply these two values, etc., things like that. And then you have control flow statements that say, if this condition is true, go here, or if this condition is false, go over there, or a while loop, or a for statement, anything that can take the flow and jump to another location within the program. So internally, the compiler represents this with the control flow graph. And the control flow graph is something that captures this structure that I was telling you about jumps. So every node is a bunch of instructions that are executed sequentially, one after the other. And at the end of a block, you have an if statement, basically. You say, if this is true, or a switch statement. If this happens, you're not seeing the slides. Okay.
Sorry to interrupt. Yeah, I think we're just still on the title slide with the.
Really?
On the left, yeah.
All right. I'll try to do it again. I don't know what happened. Yeah, it was paused. Can you see it now?
Now it's good. Yeah. Thanks.
Okay. I'm not sure what happened there. Anyway.
Yeah.
Thanks. If there are any questions, let me know. Interrupt me, and I'll try to address any issues. And if there are questions about the problem itself, please stop me. This is meant to be an interactive talk. So in this control flow graph, right, you have a lot of freedom how the blocks are laid out in memory. So, and the idea is that if you lay them out in a way that you tend to have sequential executions, then that will lead to fewer cache misses. Yeah, so with the maximum TSP heuristic, what you do is you take this graph and you take this profile information that it tells you how many times you take these jumps, and you try to maximize the number of jumps that are just to the next block in the ordering. So this was the state of the art until a few years ago. And then my co-author, Sergey Pupyrev and Andy Newell, also from Meta, proposed an extended formulation that doesn't just look at single jumps, but also at local jumps. So, and I'll say a little bit more about this, but they formulated this problem called extended TSP, and they proposed a bunch of heuristics for it and show that in practice, this leads to better performance. So what kind of performance can you get out of this? So they tested this in the real services that we have at Facebook, and the services that are compiled using this technique, you can expect them to run between 1% and 2% faster. Now that doesn't seem like a huge deal, but when you multiply it for this at the scale of a big company like Facebook, this translates into applications running faster. You won't be able to tell the difference between 1% and 2%, right? But the servers can tell, and they use less energy, right? So saving 1% of all the energy that Facebook uses in a year, that translates into a lot of savings. And that also translates into needing to use fewer servers and all the expenses associated with maintaining those servers and so on. So 1% improvement is a big deal if it comes out of just don't touch your code, just reorder the blocks, right? So that's a big deal. So this is the problem that I want to work on. And what I want to do is I want to fill in the gaps that were left in the previous papers and try to develop a theoretical framework for this extended TSP problem. All right, so let me give you the formal definition of the problem, and then I'll go over an example showing why this makes sense. Okay, so the input to our problem is a graph. In this talk, I'm going to assume that my graph is undirected for simplicity, but the same can be applied to directed graphs, which is the type of graphs that you normally have in practice, where flow goes in one direction, right? So on top of this graph, I'm also given some edge weights, and the edge weights represent this profile information that I was telling you about. So it tells me how many times I executed a given jump, right? And then we have this discount function f, which takes values from 1 to 0, and it's at 1 is 1, and at values greater than k is 0. And in between, I need to interpolate in some non-increasing type of way. And why do we use this function here? The idea is the following. Imagine that you have, ultimately what I want is an ordering of the blocks. I want to lay out the blocks in some fashion. And this is how the binary is going to be packed, right? Eventually, when you deploy these applications. So the idea is that if one block comes right after the other one and there is a jump, then there is a good chance that once I fetched the first block from main memory into the cache, I bring in a cache line, there is a good chance that the next block is already there in that cache line. So I'm not going to have a cache miss when I go and I move on to the next block. So in a sense, I get all those transitions without incurring a cache miss. So that's a good thing, and this is what we want to maximize. On the other hand, if a jump takes you very, very far away from where you were, there's a good chance that that jump leads to a cache miss, because that thing is so far away from where you are right now. So you didn't yet fetch that page. So there is some parameter K that more or less is in tune with the size of the cache lines in your system, that beyond that point, I don't get any benefit from that jump. It's all going to be most likely cache misses. So I don't want to count those. And in between, I need to interpolate. And using some machine learning, they found they tuned this discount factor, and they show that a good model is just to have a linear discount factor. So to interpolate linearly from 1 to 0. Yeah, and then you pick the best K using some machine learning, basically, the one that gives you the best performance of your model. And this sort of makes sense, because if you assume that K is your cache line, right, and then you have a jump that is of length K divided by 2, when we put these things, we don't really know exactly where the cache line starts and where it ends, right? So we don't have control over that in the compiler. So, you know, if you think about it, if these cache lines are kind of shifted randomly, right, there is only a half chance that you are within the same cache line when you do a jump of length K divided by 2. So it sort of makes sense that you would have a discount factor that is 1/2. And if you are very, very close together, but it's still not adjacent, it should be close to 1, that you get most of you avoid most of those cache misses by doing those jumps. So the model sort of makes sense. But this is the model that we're working with, and we want to understand this problem. Are there any questions about the problem itself or the motivation? This is a good time to answer questions, maybe. And if there are no questions, I can show you an example, maybe in case this was not clear. So here's a toy example. So this is kind of the input that we are getting. It's a graph. In this case, I have 5 blocks, V0 through V4. And you just here tell me how many times I execute that transition. So in this case, I go from V0 to V1 100 times. And then here I have one of these branching events that I was telling you about. So 20 times I go to V2 and 80 times I go to V3. And then afterwards, I join back here. So this would be kind of like a typical if then else statement. So I compute something, then I ask if this is true, then go here and execute this code. If it's false, else do this thing. And after I do all those things, I come back to the same point, right? After the if then else block. So this is a very typical structure of these control flow graphs. And here on the top, I have a layout. And you see that in this layout, I have these 3 edges that are these fall through branches. So these are really good because it's kind of like the default action, right? I don't need to do anything to get that edge. I only need to say, if something is true, jump over here. Otherwise, just continue forward. So in this case, these dark edges are the fall through edges, and these are the ones that I get the full amount in my objective. And these ones that I have to do a bit of a jump, there will be some discount factor associated with those. And here I have another layout, and in this layout, I have way more of these adjacent edges, right? So this is a much better layout than this one. So the question is, how can we find the best layout, the one that optimizes my Ext-TSP objective? And this is what I want to study. But before I study that, I want to try to look at some special cases to get some intuition and to tie it up to some well-known problems in the literature. So the first case that I want to explore is what happens when k equals 1, right? So when k equals 1, remember I have this discount function that is 1 at 1 and 0 at 2 or greater than 2. Yeah. So this means that in my objective, I'm just looking at all the edges, and the ones that have the two endpoints right next to one another, I get the full weight of those guys. Everyone else, I get nothing, right? And this is precisely the MAX-TSP objective. So I want to find an ordering of the nodes of my graph, and I want to maximize the weight of the edges of that tour that the ordering induces. Of course, I don't have the edge coming back. It's like MAX-TSP path. Yeah, but it's a very similar problem. Right. So what do we know? There are lots of things that we know about this problem, but there is another special case that I want you to think about, which is the minimum bandwidth problem. So in minimum bandwidth, you're also given a graph, and we want an ordering of the vertices in the graph, and what we want to minimize is the maximum length of any one jump in this ordering. Yeah, so I look at all the edges, the distance of the endpoints in this ordering, and I record the maximum, that's and the best ordering, that's the bandwidth of the graph. Yeah, so why is this a special case of my Ext-TSP problem? If I set k to be the value of the bandwidth of the graph, and I set the discount function to be 1 for everything at distance k and 0 afterwards, then the optimal solution is able to recover all the edges, right? Because there is an ordering where all the edges are at distance k, the endpoints, right? So this means that if I can solve the Ext-TSP problem, then I can solve a bandwidth problem. So this is these two observations are interesting because now we inherit some of the things that we know about this problem for the Ext-TSP, which is more general. So from MAX-TSP, we know that the problem is APX-hard. So we inherit that hardness. There are also approximation algorithms, pretty good approximation algorithms for MAX-TSP. So these we cannot use right away because they work only for MAX-TSP, but maybe there is some ideas that we can reuse from those algorithms. And then from the minimum bandwidth problem, we know that there is an exact algorithm that runs in n to the O of b, where b is the optimal bandwidth for the graph. This is a classical result due to Sachse. And then more recently, there is surprisingly a matching lower bound, in the sense that there is no n to the little o of b time algorithm, even for trees, unless the exponential time hierarchy, exponential time hypothesis fails. So, and this says that you cannot solve SAT problems in 2 to the little o of n. Yeah, so which is a conjecture that is used a lot in improving lower bounds, especially in fixed parameter tractable complexity and in fine grain complexity that is used to probe polynomial lower bounds for problems. So this is what we get. So what does that mean for our Ext-TSP? Well, we inherit the APX hardness, So it's APX-hard even when k equals 1. And we cannot expect to have an exact algorithm that runs in n to the k, even for trees, because otherwise we get the hardness for bandwidth that the exponential time hypothesis fails. So those are the negative results that we inherited from previous work. So what are our contributions? We show that Ext-TSP can be solved in trees in n to the O of k. So that sounds terrible, right? So usually problems, usually an optimization problem with trees, easy. You can solve it in polynomial time using dynamic programming or something. No, so this is, you cannot expect to get that. This is the best running time for this problem. And this result is you cannot reduce it to the similar result, the algorithm for bandwidth. You need to do a lot more work to get this to work. So even the tree case is a tough case for Ext-TSP. So that was interesting. For some special graph classes, we can get very decent approximation algorithms. We can get essentially a PTAS, a 1 plus epsilon approximation, if your graph has bounded tree width, and or if your graph is planar. Yeah, so the running time depends in n to the k, which we needed from this stuff, but also it depends on t, because otherwise you would have this harness being contradicted, right? So you sort of need that dependency there. And then for general graph classes, we have a fairly simple 2k approximation, runs in linear time, and then a k plus 1 roughly approximation that it takes a little bit more work, and but still it runs in polynomial time. And then a 2 plus epsilon approximation, and this one the running time is horrible. It's again n to the k on epsilon. So that's pretty bad, but at least it shows that for fixed k and fixed epsilon there is a constant factor approximation. Okay, so these are our results, and in whatever remains of the talk, I'll pick some of these results and I'll try to give you a flavor of them. But again, this is a good time to see if there are any questions. No questions? Okay. Again, if there is something that doesn't make sense, like, I'm using terms like exponential time hypothesis that may not be familiar or things like that, do stop me and I'm happy to elaborate. Okie dokie. Let's see. So the first thing that you can think of for any problem is to design a greedy approximation. Right, so greedy algorithms. And what would the greedy algorithm look like? So in this case, my greedy algorithm is super simple. You start from the empty ordering, and while you still have some vertices to sequence, you find a vertex that you haven't picked so far that maximizes the weight to the last vertex that you added in your ordering. You append it and you keep moving on. And interestingly, this is the algorithm of that was originally proposed for block reordering. So this was the algorithm that was used basically before Ext-TSP was proposed. So we wanted to understand what is the performance guarantee of this, and we were able to prove that this is a 2K approximation. All right, so and the observation for getting that is that if you pick a node, so if when you're going to add this node V and you look at this node U, then there are some edges in the optimal solution that you are kind of giving up on, yeah? And basically we can show that we can charge those edges to this one edge that we are picking, and the charging that you pick is at most 2K. Yeah, so this is kind of the would you give up? So you get one edge and you potentially give up 2K edges. And this may seem like a very pessimistic analysis, because it seems like when you add one edge, you are foregoing 4K edges going forward, but it actually it's K edges going forward and K edges going back in a sense. And we have a tight example showing that we can get arbitrarily close to 2K with this algorithm. So if we want better approximation guarantee, we need a different algorithm. So then that takes us to our next algorithm for Ext-TSP, which is based on finding a maximum weight cycle cover of your graph. So this algorithm is fairly straightforward. So you look at your weights and you find a maximum weight cycle cover of your graph. So this is a subgraph where all the nodes have degree at most 2. It's a collection of cycles in your graph, and you can find this optimally using matching algorithms. So then what you do is you look at these cycles and you break each of the cycles by removing the lightest edge. Yeah, so once you remove a cycle, now you have paths, and then you just sequence one path after the other. Yeah, so and the observation that we make in our paper is that the total weight of the cycle cover is at least 1 on K of the optimal solution. And so this is quite straightforward to prove. And then if you have a cycle that is fairly long, more than K on 2, then losing one edge is not a big deal, right? You're still getting most of that cost. So you are losing this factor here and times this factor, so that's roughly K plus some constant. So that's the easy part of the analysis. And then you have to see what happens when you have smaller cycles, right? Because when you have, say, a triangle, if you remove an edge, you are losing 1/3 of the cost, not this small amount, which is basically 1 on K plus 1 plus 2. So in those cases, you need to be a little bit more careful, and that's where the complications in the analysis come in. But it's also not possible to get all 3 edges if you have a triangle, right? So if you wanted to get all 3, you would have to pay some discount for this one. So then in the analysis, you show that everything works out. So the bad case is really this case where you're losing that cost there. Okay, how am I doing with time? Am I doing okay? To get a 2 plus epsilon approximation, this is in some sense the worst algorithm, because the running time is the worst, but it's a local search algorithm. You just start from an arbitrary ordering, and then you look at a stretch of size t for some appropriately chosen t, and then you try to optimize that section of the tour. So you can just look at all possible permutations. That's only n to the t, O of t, right? So that's, again, terrible, because we're going to set t to be a fairly large value. But just to understand, you know, what is possible, You keep doing this until that's no more local improvements are possible, and then you get an approximation ratio that it's 2 plus this term here, which is basically almost k divided by t. So if you make t k times 1 and epsilon, you can make this term arbitrarily small. Yeah. So, but again, you pay on the running time there, so there's the trade-off, obviously. So this is kind of like an overview. I didn't want to go into a lot of detail, but I still wanted to give you some flavor of how the algorithms that we design go. I haven't said anything about the case, the Ext algorithm when we have a tree. That's probably the most complicated algorithm, to be honest. So probably you don't want to listen about that. So instead, let me tell you about some of the future work that we have planned here around this problem. So we started with this extended TSP problem, a generalization of a couple of classical optimization problems that has a clear application to profile guided optimization. The problem had only been studied from a heuristic point of view before, and what we did was to try to develop the first steps towards having a better theoretical understanding of the computational complexity of this problem. But there are lots of problems that that remain around Ext-TSP. I'll just name the two that I find most interesting. One is to improve the exact algorithm we have to handle not just trees, but to have instances with bounded tree width. So at the moment, we can only do this with an approximation factor of 1 plus epsilon, and there is an extra 1 on epsilon factor here. It would be interesting to get this running time to be just n to the tree width times k. None of the lower bounds that we provide would contradict this running time, but I have no idea how to get there. And then the interesting result, I think, is to try to prove a constant factor approximation in polynomial time that is independent of k. Remember the two approximation that we have here, the 2 plus epsilon approximation. We need to make t huge, right? So it needs to depend on epsilon, which is, I guess, okay, because you can set epsilon to 1, but it has to depend on k too, which is not great, not in practice. Even though k is not huge, typically in practice is around 100 or 200. You know, n to the 100, that's pretty useless from a practical point of view. And if this is not possible, then getting a lower bound that depends on k for the approximation hardness. And in studying this problem, sort of, I also started thinking about other sequencing problems that are kind of interesting to think about. So, kind of, if you can think of this extended TSP, at least when you don't have these discount factors, when the discount factors are 1 or 0 afterwards. It's like trying to find a subgraph of your input graph that has maximum weight and has bounded bandwidth. Yeah, so you have a budget for the bandwidth and say, okay, I want to have the largest graph that I can possibly find. You can also do this for other graph parameters like tree width or path width. Some of these problems have been studied before, but there is not surprisingly a lot of work. And this seems like a very natural problem, so I want to toss it out there. And that's the plans that we have for future work. So to conclude, let me just recap. So hopefully you can believe me that this is the well-motivated optimization problem This is not a made-up application. The heuristics for extended TSP are used at Meta, and they're actually freely available in open source projects like LLVM now. That's an open source project for compilers. We landed that recently. And the problem has interesting connections to classical optimization problems, such as maximum TSP and a minimum bandwidth. We took the first stab at this, but there are still many problems that remain in this space. If you want to learn a little bit more about the application of Ext-TSP to profile-guided optimization, we last year we published a note in the Facebook research blog on this stuff, and it gives a little bit more background on the application. So you can easily Google it, basic block reordering, Facebook research, and you can find it. And with that, I'm happy to take questions.